Opportunity to present this research. I've got my colleagues, Hadi, who's here, raise your hand, Hadi, and Niti is a new PhD student we got. So they have been contributing to this project. So CIMIC and EIC, they are infrastructure projects, like infrastructure builders and contractors and designers. So basically we are working on utilizing the urine to stabilize our roads, airports, and so on. So it's a bit different to the rest of the fertilizer story. So I will give you a bit of introduction, what problems we have, what are the current solutions, and what's our proposal, and the plan of the testing that we are doing in this project. So what I guess we understand is that because of the increase in the population and also running out of the good lands, many of our infrastructure, including rail, road, and so on, are built on low quality ground. And one of the major issues here in New South Wales is old closed landfills. So there are a lot of old closed landfills that they used to be out of town, but because of expansion, now they are part of the cities. And these two examples that you see here, they are here in Sydney. So one not very close, not very far from here, and one in the western part of Sydney, that they are building road and a lot of bridges and so on, and the other one, the railway station there, an interchange. So, and obviously when you build on top of these types of ground, so there will be a lot of settlement, so airport or road or railway pavements and so on, they will crack. So there are techniques we like to improve them. And of course, there are other types of problematic grounds, including soft soils. I'm not going to dive too much into these ones. I guess if it's muddy land, it will settle as well. If you have got a loose, sandy material, similar you have got under the, close to the beach, I guess. So again, if it's under the ground, the buildings and roads and so on will settle. Same for expansive soils, that when there is a rain or a lot of water getting there, it will expand. That's why many buildings, particularly new buildings, they have got a lot of cracks on the walls, and same applies for the roads. And this particular issue of the expansive soil is very popular. So the soil that when you add water to it, it expands. It means your foundation of your road or building keeps going up and down. So that's why you get a lot of cracks on the structures. The current techniques to improve the landfill and also those problematic soils typically is using some materials to stabilize the ground. The most popular one is cement and also lime, so that they add them to the ground, as you can see here, mix them, so it becomes a stabilized ground. So it becomes much stiffer, you can build your structure on top. So the issue of construction with cement, I guess everyone knows that cement production creates a lot of CO2. 8% of the world carbon dioxide is because of production of the cement. So after water, concrete is the most used material in the world. So therefore a lot of cement goes there. And I won't again go too much detail, but the whole process of cleaning and converting the clay and lime into the cement is very energy intensive. So the idea that we have in this project is that for different types of materials, let's say for landfill, that's what we are starting, that Niti is working on at the moment. So what we're gonna do is that we're gonna get the urine, but it should not be hydrolyzed urine. So what was mentioned earlier, because we need to recover urea, I will quickly explain. And then we're gonna collect it from this building. We're gonna increase the pH at the moment, so to make sure the hydrolyzing won't happen. So then we will follow two passes, one using addition of the some food for the bacteria that exist in the soil or in the landfill. We're gonna stimulate the bacteria, increase the concentration of the bacteria in the soil. Then we're gonna add the urine, so it will then consume the urea and convert it to basically bicarbonate. And in addition to that, we will add a calcium, so therefore bicarbonate, which is not what I guess most of you are not interested about, the bicarbonate, because it's not a fertilizer. but then we will add a calcium to it, it will form a natural cement. And basically it will become stronger. So that's what we will be doing. So the other opportunity that we will explore is addition of enzyme rather than adding a food for bacteria, that bacteria will create the enzyme, we directly add the enzyme. So this shortens it, but then cementation happens very fast. Of course, it comes with a cost consequence if you need to add enzyme, which is more expensive than yeast, for example, which is for the food of the bacteria. The mechanism involved, as you can see in here, is that first, by addition of urease inside the soil, not outside, that's why initially should not hydrolyze, you will create the bicarbonate plus ammonia and so on, that we don't need them, that's a problem, the ammonia for us, I guess. Then we will add extra calcium to it, and it will react with the bicarbonate and then form the cement or lime, you can say. It will be precipitated inside the soil and bind the particles together, as you can see in this picture. So these are not bond particles, but here cement will be surrounding this. So therefore it will bind the particles together, it will become stiffer. May not be necessarily good, obviously, for the farming, but it is good for the infrastructure projects. So the process in here, that's what I explained. So you will have the urea, and then you using urease, you will create a bicarbonate plus ammonia and ammonium, and then you will add the calcium and you will get there. And of course we have to keep the pH high or very low. Let's say we are looking at keeping it very high to make sure the hydrolyzing won't happen, and it only happens inside the soil when we want. So the current plan there is that it will be collected, the urine will be collected from this building that Sean is organizing the visit for us later. Then we will measure we will stabilize this urine by adding the calcium hydroxide into this. So therefore the pH will go up, so it won't hydrolyze. Then what we will do is that we measure the urea content in there, and then we will filter this whole thing to make sure we just, what are the sedimented there, like such as phosphate and so on comes out of this. And then we will reduce the pH, and now we will have two liquids in there. One, we will add the extra yeast to it, which is a food for bacteria that exist in the soil or landfill. We are starting with landfill. You imagine how dirty it is, but it is on the construction sites as it is. And then we will basically increase the number of bacteria in the soil by giving this food. Then when this process finishes through another channel, we add this urine plus the calcium chloride or calcium hydroxide. Both of them can be used as the mechanism to cause the cementation, and bacteria is in there to basically break this urea into the calcium carbonate that we need. And the test we will be doing this one is one of the tests that we will push the liquid through the soil, as you can see, and then we collect it on top. So by doing it several cycles, we can keep increasing the amount of cementation that happens in the soil. So usually one cycle won't do it. We need more deposition of the cementation there to make it stronger. So, and this is a list of tests we will do. So the base materials we will use. First one is the landfill material we have collected from one of the construction sites here in inner west of Sydney. Also, we will collect some Brangely shale from the new airport being built in western part of Sydney for stabilizing the runways. And also we will do a test on the sand as a benchmark. And the materials or additives for the treatment, of course, will be treated urine plus lime and cement as the benchmark to see relative to those ones how good they are. And these are the bunch of tests that you can see. Typically they are the mechanical tests to measure strength and stiffness of the material we have. So one of the issues there is creation of the ammonia byproducts there, which is not nice obviously for us. So we will explore a few avenues, addition of natural zeolite, basically to remove the ammonia, or we will try to immobilize it, means it's there but it won't move, or we will do a simple drying process basically to get rid of ammonia on site. So here we are talking about areas of tens of kilometers or hundreds of kilometers. So basically these are large projects. And of course, maybe that ammonia can be collected for hydrogen generation and so on. So and the benefits will be reduction in the CO2 through the reduction in the use of the cement or general purpose cement. And in many developing countries or underdeveloped countries, actually the cement is not there. So even if they want to use it, they don't have access to it, but they have access to the actual urine there. And of course, this will also improve the image of the construction industry, which is not that great, I guess, in terms of CO2 emission. And the project will address also sustainable development goals of the United Nations, as you can see, from infrastructure, reducing inequity, sustainable cities, and so on, that you can see. So thank you very much. And that's the oh yes, sorry, I have still one more slide. So what are the possibilities for collaboration for us? I would like to really explore these opportunities. One possibility there, if you can think of something, is that if we can have access to a concentrate of urea, which is not hydrolyzed, this will definitely help us to, rather than using several cycles of treatment, use one cycle. So if some of you work on the concentrate of urea, we are so keen to see how can we get that. Of course, on use of other stimulation solutions or the food for bacteria, we like to work, minimizing generation of ammonia, and of course using other types of materials for improvement. But the first one, what I just have identified is this urea concentration. If there is someone working there, I'd like to hear more. And thank you very much for listening to me today.